they have those cars where people can fill it with old chicken grease.
Oh, right. That would
It
be
smells like fried chicken going down there.
I don't mind that.
I know, right?
A lot of people following you though.
Yeah.
A lot of hungry people.
Yeah. 5 o'clock traffic. What smells like chicken?
That would be funny. I love that. All right, continuing on in Unit 3, we're going to learn about cis-trans isomers. So we've seen isomers already, right? The structural isomers, also called constitutional isomers. They have the same molecular formula, different structures, different names. With these isomers, they also have the same molecular formula. So I'll put same molecular formula. Kind of the same name. I'll put same name. And you'll see in a second why I say that. Same name. Different structures. Cis-trans isomers only can occur with alkenes. Okay, so has to be on alkenes. So what is an alkene again? Carbon-carbon double bond. Very good. So 1,2-dibromoethene is an alkene. It can be written two different ways. This is an example of a cis-trans isomer. So when you think about dibromoethene, two carbons in the parent with a double bond between the first and the second. Then off one carbon, and I'm going to draw this as the complete structural formula. The other thing about cis-trans isomers is they're usually drawn explicitly. And when I say explicitly, like the complete structural formula. You know, so if you think about these explicit lyrics, you think of the words they use, think of the structure as being drawn very explicitly to show the relationship of those bromo groups to each other, or whatever group you're talking about. So 1,2-dibromoethene, what's bromo? Br. Okay, so you're drawing these explicitly. And then on the other carbon, you have the hydrogens on, or off each carbon, other bonds. So these bromo groups are across from each other. So this is, so if you think about a transatlantic flight, what are you crossing? The Atlantic Ocean. This is the trans isomer because these bromo groups are across from each other. So this is trans 1,2-dibromoethene. The other isomer of 1,2-dibromoethene is cis. And if you think about sisters, most of the time they're close, right? I'm sure there are some examples where they're not close. Or this is cis. I have a friend, she and her sister are so close. They're, best friends, above husband, above anything else. They're very close sisters. So I always think of, that type of relationship when you think of cis. Cis 1,2-dibromoethene. So this is an example of cis-trans isomers. The definition, different arrangements of groups on the two sides of the double bonds.
So this can only occur in the smaller structure?
For our purposes, yes. We keep it simple. There are, and when you get into higher level organic chemistry, there's something called the EZ isomers, where you can have a huge structure and double bonds, and then you have to do the ranking, priority, what's across. We don't get into that. So for our purposes, we try to keep it pretty simple. But the main thing with cis-trans isomers, they only exist if you have two substituents which are the same and they are on different sides of the double bond. So for our purposes, we keep it simple. These structures down here that I have, can any of these be cis-trans isomers? So if you look at this example, this is just ethene. There are no substituents. And there's no way to tell if this hydrogen is different than that hydrogen. So you cannot have cis-trans isomers with that one. Now, on this next example, this is 1,1-dichloroethene. You do have different groups, but you see they're not across from each other. So if this was arranged differently, if this, instead of being 1,1, if it was 1,2, so 1,2, yes, 1,1, no. So, like the one we just saw, you see how that was 1,2 dibromo, and we're able to do the across. This one is on the 1,1. The chloro, so they're not on opposite carbons, so they're not across. Right. So this one is a no as well. Now, in a higher level organic chemistry, that you could do E and Z, but we don't do it in this class. So because this doesn't have two of the same substituents across that double bond or on the same side of the double bond, no. And the same thing here, with bromo. You don't have anything that's the same. So that's another no. So as long as one of them is as the same across that double bond, you can have cis-trans isomers. Let me give you an example. I'll just the orientation of those double bonds, yeah. Now, if I change this one ever so slightly, and I had 2 bromos here, would that be yes or no? Yes. And would it be cis or trans? Cis. Yes.
So this one would be trans and two.
Yes, so you do have to specify cis or trans in the name. That's why I say same, kind of in wavy. It's not quite the same because you have to specify whether it's cis or trans. But the rest of the name is the same. 1,2-dibromoethene. The only difference is the cis for the trans. All right, so when you're taking a quiz or an exam and you're asked about cis or trans isomers, be aware for the suggestive format. You wouldn't be able to tell whether this was cis or trans if I had it written like this. You see what I'm saying? It has to be written with a complete structural formula. So when you're asked to name an alkene and it's written like one of these, that's when your cis-trans sensor should be going off. Look, is it cis-trans? Can it be possible? If it's possible, then you need to put cis or trans on it. So this structure here, just like before. Now, a lot of students, when they get to cis-trans isomers, they think, oh, I see it's a cis-trans isomer. And then you kind of forget all the other stuff you learned about naming. So remember, with alkenes, it's the longest continuous chain of carbons that contains the double bond. Just because that double bond is written explicitly right in front of you doesn't mean there isn't something else attached to it. You see? There could be carbons coming off of that, and that could be part of your parent chain. So a lot of times students will circle these two carbons and say, that's ethene. I'm sure of it. I know it. I'm convinced. And it's a cis-trans isomer. I'm going to get full credit on it. But they forget to look to the left and right of this. Are there other carbons? And there are. So what is the parent in this one? Butene. And you have to tell me where that double bond is. So 1, 2, 3, 4. So 2 butene. And what's coming off the second and third carbon? Right. 2 fluoros. So it's 2, 3 difluoro. You think, shoo, I'm done. I've named it. I've taken care of everything. But you've forgotten to specify cis or trans. And depending on the point allocation, if this was a 3-point question and you forgot cis or trans, it could be a half point or 1 point off. So a lot of little things to keep track of. So this is definitely a nitpicky unit. Make sure you check everything and go back. And the more you practice, the better you will get at it. So is it cis or trans? Cis. So cis 2,3 difluoro 2 butene.
And so you can only have cis or trans on a double bond or above.
Right, and it double bonds. So we just see it on double bonds, not triple bonds. And the reason for that, we really don't get into it in this course, but triple bonds are linear. There isn't a cross. We're going to be building the models of these so that you'll see, and actually, I'll show you right now. So, with your model kits, all right. So I have a methyl. So in the next lab exam, instead of Bunsen burners with strikers, you'll hear the popping from model kits. And so let's just call these fluoros green. So you can see the double bond, has this geometry about it. So these are 120 degrees separated. That's the bond angle. Now, when you get into alkynes, what you see, and you don't necessarily see this when you draw this on the paper, you see it a little bit because I always draw them like this, but this is an alkyne. This is 2-butyne, 1, 2, 3, 4. So that's why.
Bonds pulling it in.
So that's why you can't have the cis in the trans. So only with the alkenes. And notice with these alkenes, I can't just rotate this to get it from cis to trans. It won't go. I actually have to break the bond. I have to break 2 bonds. And now I have trans. Okay. So, like I said, when you see this on the exam, you see alkenes written suggestively. Don't forget all the rules of nomenclature. Don't just, oh, I don't have to worry about that. So with this alkene, find the longest continuous chain of carbons that contains the double bond. So how many would that be? 6. Good. So 6 would be hexene. What hexene is it? 3 hexene. All right, I'm going to name this. You tell me if I'm right. 3,4 dihydro 3 hexene. No. But I get students. Oh, wait, I forgot. It's not right because I didn't add trans. Trans 3,4 dihydro 3 hexene. What's wrong with that? The hydrogen's what? Right. Yeah, they belong to the carbons. You're just we were just showing you the hydrogen-carbon bonds so that you would know that we're cis or trans. We're not trying to say that this is a special group. This is just like all the other hydrogens on these carbons.
So it's not cis or trans.
It is trans, but instead of being, it's not the hydro. So trans 3 hexene would be the name. Yes.
You do trans and cis with hydrogens and everything else but carbon.
Well, you could do carbons too. You could have something like as long as there are 2 groups that are the same, like you could have this.
I don't know.
Anytime you have a double bond where there are 2 groups that are the same across that double bond, then you can have cis or trans. Other questions? All right. Well, let's. What's that? You have a question?
Okay. So that one you just grew.
Mm-hmm.
So your parent chain would be from this top all the way there. Okay.
Mm-hmm.
So one would be like cis, something dimethyl.
This one would be cis 3,4 dimethyl 3 hexene. So when you see a structure like that, and it's just written explicitly like that, think cis or trans. If you're asked to draw a cis or a trans, start off with your butane. Asked to draw cis or trans. Start off with that. That is what you build from. Sometimes it helps to, have just your condensed structural formula written out, and then you can kind of zoom in on that double bond. Like if I have, let's say I have 2-butene. So this is 2-butene. The way it's drawn, you can't tell whether it's cis or trans. In order to show that, you need to kind of zoom in on this bond right there. So you zoom in on that bond, and you figure out what's attached to those carbons in the double bond. And you'll see that there's a hydrogen here, a methyl group. So if you put hydrogen, methyl group, and then the same thing is on the other carbon, hydrogen, methyl group. Which isomer have I drawn? Cis. So this would be cis to butene. Does that kind of clarify how we're getting this? It takes a little bit of practice, in seeing these. So work your homework problems, your practice problems, your practice exam. I have that as well. So the more you see this, the more second nature it will become. So the next part of this unit, we talk about addition reactions. And addition reactions involve alkenes going to alkanes. So the main thing is your double bond, whether it be cis or trans, your double bond goes to a single bond, but you've added something. So I put AB, so now you've added A, B across that double bond. So what has happened to your double bond in this process? It's broken. It's gone away. So your double bond is no longer. So your double bond goes to a single bond. Bless you. So in these reactions, on the exam, if you provide a product that still has a double bond present, you won't get any credit. So you have to make sure that your double bond goes away. So this is just a very general example. You have your alkene, you have X and Y, and we'll learn different reagents. So your double bond, your alkene into an alkene. What's the substitute of alkene? What's that? Not for that one. We'll do more specific examples. That I'm just trying to keep it as general as possible so you don't get caught up in whether they're hydrogens or not. Alkene becomes alkane. So your ene goes to an ane. All right, so I want you to just draw the condensed structural formula of 2-butene. I want you to draw it 1, 2, 3, 4 times. Condensed structural formula. So we're going to learn 4 types of addition reactions. And I don't want you to get too wound up about this. I want you to get, oh my gosh. If you keep it simple, you will always get these right. Remember what changes in an addition reaction. What happens? The double bond goes to a single bond. So you're looking in every one of your 2 butene molecules, this double bond is going to go away. So even right now, you could probably complete these reactions. So everything else in that molecule is going to stay the same, except that double bond. The double bond goes to a single bond. So I want you to copy down So copy down your new molecule without the double bond. And we'll fill in the rest in just a second. The only difference between all of these reactions is what you add across that double bond. With hydrogenation, you're adding hydrogen across that double bond. So I'm just going to draw a line down, and what will be coming off of it? Hydrogen. Good. With halogenation, this can be any halogen, whether it be chlorine, bromine, fluorine, or iodine. So X could be chlorine, bromine, or iodine. So you're just going to put your X coming off of here. Hydrohalogenation is hydrogen and a halogen. So you're going to have H on one carbon, X on the other carbon. Doesn't matter. It does not matter which right now. In a little bit it will. And hydration is just adding water, HOH. So sometimes with hydration reactions, you'll see the reactant written water, H2O. I always encourage students to cross it off and write HOH. So then it's more explicit what's going to be added across that double bond. You're adding H to one carbon and OH to the other carbon. So for your reactions for Unit 3, this is what they are. They're pretty straightforward. In Unit 4, they get a little bit more complicated. You know, the reactions that we see for Unit 3, we also have the combustion reactions. Remember the incomplete and the complete combustion? But we have addition reactions. And if you completely blank on this part of the exam, and you just step back and you take a breath and say, wait a second, I don't need to be hyperventilating about this. I know that the alkene gets converted to an alkane. So if you just zoom in on that alkene and then make it to an alkane and then add those two things, it will take you a long way. Yes, there are 4 different types of addition reactions, but the basic principle is the same. You're always adding something across that alkene.
Will it say like will it just be written out like a question like is a halogenation reaction and
So-
or will it have like the
You could see 2 types of questions. You could see true-false questions. And true-false questions and multiple choice questions involving the name, knowing what's involved helps you. You know, I always encourage students to make flashcards or practice sheets, but what you can do is have a sheet of paper that you fold in half, and I know some of you do this already, where you know you're on one side you have the reactants, on the other side you have the products. Or you could imagine doing this for each reaction. You know, on the front of the card you have the reactant, on the back of the card you have the product. And you can have the names as well. But for true, false, and multiple choice questions, what we're going to do is ask you, you know, in hydrogenation, you know, what is added? True, false, you could see. Hydrogenation involves adding water across the double bond. I said hydrogenation, not hydration, right? So that would be false. So it's important to know what atoms are being added across in each one of these reactions. That's for the true, false, and the multiple choice. Then there is a short answer portion where we have reactions involving the arrows. And so we will leave the product blank, and you are expected to fill in the product. And, you know, like I was saying, knowing that alkenes go to alkanes will take you a long way. Okay. So on the next page, I have one, two, three, four. This is 2-methyl 2-butene. So this is twice. 2-methyl 2-butene. Is that a symmetrical alkene? I haven't talked about symmetrical at all. But think about what symmetry means. It means the same on both sides, right? So our example previously of these reactions dealt with 2-butene. And 2-butene is lovely, isn't it? It's so appealing to look at because it's symmetrical. So 2-butene is symmetrical. It's the same on the left and right. 2-methyl-2-butene is asymmetrical. It's not the same on the left and right. Unsymmetrical. So I'm going to put unsymmetrical, unsymmetrical. Now, what we're adding to 2-methyl-2-butene, is it symmetrical or unsymmetrical? Unsymmetrical, right? It's not the same. Water, HBr, so I'm going to put unsymmetrical, unsymmetrical. Now I'm going to give you the products. So you can just watch me do this. And I want you to watch to see if you can figure out how I'm going to add these, if there's a trend. But just like I said, it were the only thing that has changed. This double bond has gone to a single bond.
Is it because you're trying to make that CH2?
Yeah, that comes into it, yeah. Goes with the hydrogens. So, do you notice a trend in how I added these two unsymmetrical reagents to these unsymmetrical alkenes? Flipped it. So the hydrogen always went to the same place, right? So, yes. So Markovnikov's rule. I'm going to change this up a little bit. So, when unsymmetrical reagents are added to unsymmetrical alkenes, hydrogen always goes to the carbon with more hydrogens. So when unsymmetrical reagents are added to unsymmetrical alkenes, H always goes to the carbon with more hydrogens. And in this, I'll wait for you guys, I know you're still copying. So in these examples, 2-methyl-2-butene, the carbon in the double bond that has more hydrogens is right here. So the hydrogen in your unsymmetrical reagent says, hey, I like hydrogens. I'm a hydrogen. I want to go to that party, right? I want to go to where my friends are. So that's why hydrogen adds there. So hydrogen always goes to the carbon with more hydrogen. Likes to party with their friends. So, you know, if you think about your friends and who you like to hang out with, you probably have a lot in common. And so the hydrogen's no different. They want to be with other hydrogens. Questions on this? Okay. I want you to work on these reactions, and you don't have to think about this rule. This is called Markovnikov's rule. I don't think I said it yet. You don't have to think about it unless you have an unsymmetrical reagent reacting with an unsymmetrical alkene. We did not even mention Markovnikov's rule. It only applies to unsymmetrical reagents, but it didn't apply to 2-butene because 2-butene is symmetrical.
And you always do your symmetrical from where the double bond is.
Mm-hmm. So remember, with all of these addition reactions, if you're getting tripped off, these are alkenes, they're going to be alkanes. Alkenes going to alkanes. The chemistry occurs at the double bond. So all you do is see, and you can flip these hydrogens around, CH2, CH, CH, CH3, CH3. So this one, you're adding H2. And you'll see sometimes the catalyst written above for hydrogenation. The reaction doesn't occur without the catalyst, but we would never put anything, we wouldn't expect to, if it wasn't there, we wouldn't, oh, it's not going to happen. We will put it there. So if you see something written above the arrow, don't let it trip you up. It's still an alkene going to an alkane. You're adding H and H across that double bond. And if you wanted to, you could write this, and this happens after you practiced a little bit more. You could say CH3, CH2. But see how that double bond is no longer intact.
So that catalyst is breaking that double bond and it's adding hydrogen to each one of those.
Right. The reaction is, and the catalyst aids in that. The catalyst gets returned to its original state, but yeah, it has to be there. What was your question, Josh?
CH3 on the first carbon.
Nope, you can say CH3 and then CH2 on the second carbon. If you want to condense this carbon-hydrogen bond down, go for it. So, with 1-methylcyclohexene, you erase that double bond. You add bromine, one here and one here. If it's difficult for you to see what is to be added across the double bond, you can always cross out Br2 and write Br, Br. You can do the same with H2, H, H. I sometimes have students who will suggest we'll write This is the structure. But see how that bromine is not getting added across the double bond? It's very easy to do impossible chemistry on paper. That never happens like that. But on paper, you don't have that immediate feedback. This reaction is not going to work that way. So that is incorrect. So, especially when you're starting out practicing these reactions, cross out your reagents and write them more explicitly. And on the exam, you can write all over it. All right, so these last two, we have, the first two we had symmetrical, so we don't have to think about Markovnikov's rule. These last two, we have unsymmetrical reagents being added. If you have unsymmetrical reagents being added to unsymmetrical alkenes, then you have to think about Markovnikov's rule. This is an unsymmetrical alkene. So both of these you have to think about Markey's rule. Or the hydrogen. Where will the hydrogens go? Where is the better party on these two carbons? So when you identify a reagent as being unsymmetrical and then the alkene as being unsymmetrical, pick the carbon in that alkene that has more hydrogens. This is where the better party is. So the better party for hydrogen is this first carbon. Does that make sense? Question? This last one, we have an unsymmetrical alkene, we have an unsymmetrical reagent, addition reagent. It is not very apparent with this geometric formula to see where the better party is. So you actually have to go through each carbon in that double bond. 1, 2, 3, 4. This has 4 carbons bonded to it. Are there any hydrogens on that carbon? No. No party there, right? This carbon here, 1, 2, 3, has 3 bonds explicitly shown, so that must mean that 1 hydrogen is implied. So this carbon is the better place for that hydrogen to go. So that's Markovnikov's rule. So you're going to have your chlorine go to this carbon. You can draw it like this. You don't have to explicitly show those hydrogens. If you'd like to show them more explicitly so it makes more sense to you, I will definitely accept both answers. And in the beginning, I encourage you to write them out. So I would accept that. So this hydrogen goes here, this chlorine goes here. questions on these? If you added the chlorine to the other carbon, if you flip this around, I would give you half credit. So, being incorrect about which way it adds, but you're still adding something across that double bond is worth, if this was out of 4 points, worth 2 points. So, the underlying principle of all these reactions is that alkenes get converted to alkanes. And, if you want to bring your highlighter to the test and highlight those double bonds and say, okay, this is where everything's changing. Everything else stays the same. Okay, the last part of Unit 3 deals with aromatics. And remember, aromatics are looks like a cyclohexane, but then it has alternating, double, and single bonds. So this is benzene. It's an aromatic. How many carbons are in benzene? 6. How many hydrogens does benzene have? How many hydrogens? 14. Count each one. Remember, each line intersection represents a carbon. I'm almost done. You want to say 6? Good. I'll show you.
Without the bonds of CH2, 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 and then let's say on a bond, each different, that's CH2 to CH, right?
Right. So I'm building this so you can see. That is benzene. Has 6 carbons, 6 hydrogens. 1, 2, 3, 4, 5, 6. And that's because on each carbon there are 1, 2, 3 bonds already in place, and then 1 hydrogen coming off. So it has 6 hydrogens. So benzene is an aromatic hydrocarbon. It can be written many different ways. That's because in benzene, all bonds are equal. They are halfway between a single bond and a triple bond. So your drawing of benzene is kind of a snapshot. You just caught it at that second. And then in the next second, those double bonds are rotating. They're going the other way. And then they're going back, and they're going the other way. So you can have your benzene written like this. You can have it written like this. And they're the same.
So the actual bonds are moving, or just
The electron density. Right. For our purposes, the bond length and the bond strength is the same. So all bonds are equal in benzene. And that's why drawing benzene like this means the same thing. So it takes care of those alternating single and double bonds. So I encourage you to find a way that is comfortable to show benzene. If you like doing alternating single and double bonds, go for it. If you like the circle, go for that. Just be aware that this is not the same. This is benzene. This is what? Cyclohexane. So be careful with that. The other aromatic hydrocarbons that you need to know for exam 3 are on the 3 orange flashcards. Toluene, that has a methyl group, and this is always number 1. And naphthalene, two benzene rings fused together. How many carbons are in naphthalene? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or sorry, I said 10 and then I wrote 9. C10. How many hydrogens are there? All right. 1, 2, 3, 4. 5, 6, 7, 8. Does everybody see why there are only 8 hydrogens? Those 2 carbons that are fused together, they have 4 bonds already. So they can't have more than any more hydrogens. So naming aromatic hydrocarbons. When you see a ring with alternating single and double bonds, or the circle, and that's the only thing, there isn't a longer chain. There isn't a chain of 8 or a chain of 10 or a chain of 7. The parent is benzene. So the IUPAC name for this one would be benzene. That's the parent. And you're just going to name the substituents like you did. Now this is 1, 2. If the double bond was flipped around, if it was written like this, it would still be 1, 2. Because remember, the bonds in benzene are all equal. They're always moving around. So if you took another picture of it, the double bond would be rotated the other way. So kind of have to shift out of the mode of, the double bond has to be between carbons 1 and 2, which is what we saw with cycloalkenes, but that does not apply to aromatics. So this is 1, 2 still. So this will be 1, 2 difluorobenzene. That's the IUPAC name. There is a common name when you have 2 substituents on a benzene ring. And it's called ortho. The common name is almost the same as the IUPAC, but instead of numbers, you just say O. O difluorobenzene. So these common names, ortho, meta, and para only apply when you have two substituents. So like this isomer here, M-difluorobenzene. The next one is P-difluorobenzene. So the IUPAC name from M-difluorobenzene would be what? 1,3-difluorobenzene. And then this one would be 1,4-difluorobenzene. Para.
So you just use that ortho, meta, and para to just like the shape to tell you where those
Right.
groups are going to be.
It's kind of like there are always older names in chemistry before IUPAC came into existence. So it's good to be aware of some of the common names, like isopropyl alcohol, for instance. You hear that all the time. That's a common name. The IUPAC is 2-propanol. So you don't hear that as often. So that's why different points will teach you the common. Okay. On the next page, name the following according to IUPAC rules. So, I'm going to go through a few of these with you because when you have a benzene ring with a methyl group, the parent is toluene. That carbon is always number 1. So this is 2, 3, 4, 5, 6. What is NO2? What group is that? Nitro. So 2, 4, 6. 2, 4, 6. Trinitro-toluene. And I know I've given this example before. This is TNT. So, now this structure here, what do you see as the parent? I've heard meta. I'm glad you said meta. Toluene is the parent, you're right. Meta cannot be used because how many substituents do I have coming off of here? 3. So you can't use meta if you have more than 2 substituents. If you had 2, you could use it. But so this is, toluene is the parent. This is carbon 1, 2, 3, 4. This is 3, 4 dichlorotoluene. I don't have to say 1 toluene. Now this example here, I do have 2 substituents. How are they related to each other? They're what? Kind of, but are they ortho, meta, or para? Ortho. So they're ortho. So you could say O. Now what's the parent on this one? Toluene. So this is toluene. What's coming off? Sec-butyl. Very good. O, sec-butyl toluene. Right. So we could name this a few different ways. I appreciate, yes, thank you for pointing that out. So it,
Don't confuse me anymore.
no, I'm sorry about that. It is a common name. I wanted to point it out too because it has two substituents. And you can see this with toluene. So the correct answer, if I said it has to be IUPAC, would be 2-sec-butyl toluene. Does that make sense? IUPAC recognizes that benzene ring with a methyl, the parent is toluene. Right. But if we ask you to name a structure on an exam, we either say common or IUPAC. So I would accept either. Now once we get to this point, and I know you guys have had a long week, tired, cross-eyed. A lot of times students will say, oh, I know this one. This is para-methyl toluene. No, why not? I'm not sure. You know it's not right. No double bonds. It's a cyclohexane. So can't I just say, I learned this new way of naming. Can't I just say para-dimethyl cyclohexane? No. Ortho, meta, and para only apply to aromatics. Okay, so only applies to aromatics. So it's not para. What would it be? 1,4. All right, so I want you to draw these two structures now. Okay, so 2-phenyl, 1-heptadiene, and on these I didn't ask you to do condensed. So you can do skeletal, 2, 4, 7. Okay, and O-chloromocaptobenzene. And yours could be rotated anyway. Just as long as the relationship between chloro, Cl, and SH was 1, 2. So if you could imagine drawing a little O between there, then you have the right relationship. I do want to say one more thing before we finish Unit 3. Benzene versus phenyl. Benzene is used when the parent is 6 carbons. Phenyl is used when the parent is more than 6 carbons. Yeah, I'm going to do the names. So sometimes students get confused about benzene versus phenyl. And they'll say, shouldn't this be 1-phenyl propane? No. This is 3 carbons. This is 6 carbons. 6 carbons wins. So it's 3 versus 6. 6 wins. So it should be propyl benzene. Now why didn't I say 1 propyl benzene? It's always going to be 1 when there's 1 group attached to benzene. Okay, this one, a lot of times students say, well, why shouldn't it be, I don't know, heptyl benzene. Crazy. This is 7 versus 6. 7 carbons wins. So it's going to be 2 phenyl heptane. So hopefully that clears up any questions you have.
They're the same chemical structure. They're just based